then you can you have done really well. You can the whole setup and do the results again.
Yeah.
Because last people will be getting. That means great doesn't mean you can discuss and finish. You can some of the
Yeah, was it you that was with me? Or was it Deepak where he came and we were getting the data? Was that you with me? Not Deepak.
Deepak.
Yeah, he was with me and we were getting really good looking data.
Yeah.
So he's like, oh, this is you do better. It's like I literally told him, like, I thought you'd be happier. What's wrong with you?
Yeah, I remember that you were told that. Yeah. No, in Friday evening he was also happy about the data and he told you that we can publish everything. Today, I was expecting something like this.
Yeah, he comes to me today like, I don't know what to do. That's like, why the fuck was I not here?
Even Dustin will come.
He's here, right?
He's here?
Yeah.
Yeah, I think he came Saturday.
Yeah.
Yeah, he takes. He will come school today. Maybe he wants to remove the old things and that things like that. We contribute to the part.
Yeah.
Dustin, did you tell us also?
Like this week's sending and last week gives like.
Oh, the Dustin sending.
Oh, he's going to send them?
Yeah, this Friday that so that's when he was here.
You know, that's another.
Yeah, Friday.
Oh, no. You know what he's talking about?
No, I think today morning we did it.
We talked about Dustin's seminar,
Yeah, that.
triply periodic helical structures.
Yeah.
Oh, okay.
Yeah. Thing. We have a homework due Friday.
Oh.
I'm saying,
No, nothing good.
It's like stories.
So there is a small change in the quiz submissions. Till now, you have been submitting on D2L. From now onwards, starting like today, you can submit it online, but from now onwards, you submit it in class right before the lecture, like at this point. Is that clear for everyone? Right, quizzes due in class. And this is that means the quiz that I'll give today will be due in class. Basically, I'm not able to read them. Like I go to D2L and it's after 2 weeks or something. So it's not really productive. Earlier, I used to do it submissions in class and it was much faster and I used to read it properly. So I think it is more productive to submit. There's a midterm 2. When is midterm 2?
31st, that's next week.
So
We got
next week?
No.
week after 31st.
Yeah, so that's a question. When is the midterm?
Halloween.
Huh?
Halloween.
Halloween? Oh, 31st?
Yeah, it is.
Okay, because there was an email circulated saying that it is, I think Pooja wanted it to be 1 week delayed. And then Pooja is changing it again. So it's going to be October 31st. Is that very clear?
Yeah.
Okay. Yes, the clear October 31st.
Maybe one question take home.
Hmm?
Only one question take home.
Oh, I don't know. Okay, so. I guess you would like it like that. Is that the preference?
We like that.
You like that? Okay. Yeah. So we'll have one question take home. No? Or one or more questions take home, how about minimum one?
I like that better.
Yeah. Yeah, I think, yeah, my concern with that is that I'm not seeing a immediate correlation between the homework grades and the midterm grades. So, and I trust midterm grades more. So that's the only reason why I'm depending, or usually by this time I switch to take home exams if there is a clear correlation. But I don't see that correlation, so I have to depend on midterms. Okay, we were doing Fourier transformations, and as far as the actual definition of Fourier transformation goes, I've already provided it to you. There are homework examples on that, but today I'll do something concerning electrodynamics, which I think brings out the idea of Fourier transformation and the need for Fourier transformation, at least in physics, very clearly. So we will discuss mostly polarization, which is probably, you see that in the first course in physics, most of you. But let's do this more precisely, and you will see even simple things that we take for granted in Fourier in a Fourier space can be tricky. So let me first define a Fourier transformation. So this is transform or transformation. So usually we have a function f of x, and let's say Fourier eigenfunctions. This is eigenfunctions should always be thought of as unit vectors in your three-dimensional vector space, but now we are in infinite dimensional vector space. This is e raised to I k x. X is the actual space variable that we have, and k is the Fourier transform variable. So usually we have to define what are the constraints on this. In this case, it is let me work in time. Okay. And when you work in time, you usually introduce a minus sign that is mostly to work match with the idea of Lorentz transformation, where space and time have a sign difference. And so t is minus infinity to plus infinity, and omega also is minus infinity to plus infinity. In this way of when the moment you put in time, there is a slight difference with respect to position, in the sense that this is future now, and this is past. And usually you cannot access the future, right? That's our general idea, that we don't know what our future is, for that matter, even particles' future, even when we write down equations of motion for a particle, we don't know the future, but we can predict it to a certain extent. Like that's what we would like to see. How much can we do that? So that's Fourier eigenfunctions. And if you have any function f of x, any function, right, you can expand this in terms of your Fourier eigenfunctions, and this is given as omega over 2 pi. 2 pi is a constant you put in, and these are your unit vectors, your I minus I omega t, and these are the projections of the function in the direction of the eigenfunction. They are omega dependent. Again, I would encourage you guys to visualize this at least. You have eigenvectors EI. You have I. That's your vector A. And this here I runs from 1 to 3. Right? This is your eigenvectors, 3 eigenvectors. I hat, J hat, K hat. That's your component. This we have a very good intuition for. It's practically very same thing here. That is a unit vector. Summation now is over infinite variable, infinite and continuous variables, and these are your components of this function in the eigenbasis of Fourier eigen. Usually, you would like to get, once you have this relation, you would like to know how much is the component in terms of A. So you want to, this will be the Fourier inverse. If you want Fourier inverse Fourier transformation, if I define this, what is my Fourier transform, Fourier, let's say components, then we would do, this is the x times e raised to I omega t times f of x. You can do this directly here. If I were to integrate this function after multiplying with e raised to I omega t, you can derive this expression, but that will require orthogonality properties of the exponential or the Fourier eigenfunctions. But these two are the basic ideas. And I again wrote x. I think I mixed up, right? What's the mistake in here?
Instead of dw, it goes vice versa, right? Dx.
Again, louder.
So instead of dw by we see
No.
the dx.
No, this is okay because this is the integral variable. I can call it anything. This is a time dependence, but I wrote it as x dependence, right? So this should be,
Oh, yeah.
and then here again, same thing. So that's it. So we have time dependence. It's good to ask if you have all possible components, like for example, if all your 3 AIs are 1, right? So then what is a vector? So there is a unique vector when all the components are exactly equal to 1. That means they are coming with equal weight. Like that's one way of asking it. So you can ask, what is the function that you have here? So this is all you need for the transformation, but just an information is there is a very specific function. My question is, what is this equal to? If for every frequency, this is equal to 1. Yeah, that's actually a good way of seeing this. This could be a color. This is the amplitude of that color. We always talk about red, blue, green gives you white. Is that correct? Red, blue, and green in the unequal amounts gives you white. Here we have all the the whole electromagnetic spectrum for us. And the idea is, what is the color you will get on the left-hand side? Here, it is time dependent, but I'll bring out the color more clearly as we proceed. Now we are asking if I give equal weightage for every color, omega frequency. Frequency is the color, right? What exactly will you get in here? Is that familiar? Don't think in terms of color stuff mathematically. Have you seen this expression before? Get rid of the one, maybe that is more familiar. So that's a delta function. So I think this was when we were doing delta function. we found many representations of a delta function. And one way of looking at this is that if t was equal to 0, right, remember this appears only when t, this contributes only when t equal to 0, which is infinite, otherwise it's 0. And if t was equal to 0, this is an exponential of 0 is 1. This is an infinite integral, minus infinity to plus infinity. And if t was not equal to 0, these are oscillatory integrals. That's a tricky business because these are going from minus infinity to plus infinity. You have to be more careful about that. But for our purposes, these are oscillatory integrals, so that goes to 0. And it is either 0 or a 1. And you can show that if you integrate this with respect to t, this will exactly be equal to 1. So this will be our delta function representation. So this is a delta function. Yeah, let's just say delta function. How will a delta function look like in Fourier space? So you have a function which is pure, and pure in the sense that there is only one point that contributes to that. So if we all have a field for delta function, it's 0 everywhere. At one point it goes to infinity. That is that clear? Now, if you have such a function, what is its Fourier transform? How many components do you need? Right. What is the Fourier transform? Like that is 1. Like f tilde of omega is 1. Let's check that. So f tilde omega, which is 1, right? F tilde, like, let's write it as 1. That will be equal to minus infinity to plus infinity, dx e raised to I omega t of delta of t. Is that correct? How do you evaluate delta functions? Is that really 1? What is this integral equal to? How you evaluate delta functions is, remember, wherever delta function goes to 0, the argument going to 0, here t is equal to 0.
So you need that.
So I have put t equal to 0 everywhere else.
So it's just the integral of 1.
Yeah, I think I'm messing up everywhere. Maybe that's the confusion. So this is t, right? So maybe that's why you're not answering. That's t. So if I were to place t equal to 0 there, then that's 1. So that's integral, and that's your R1. In quantum mechanics, we usually say that position and momentum cannot be measured. If you measure one thing, there is an error in the other. That's equivalent to saying that if you were to expand this a little, this is a delta function, right? This is very squeezed, right? Position or time here. Time has been measured pretty precisely. That's what it means. Right? In the extreme sense of delta function, you have exactly measured position or time in this case. What will happen to its Fourier transform? Let's say in this case frequency, otherwise we say momentum. This will spread out. This is 1. Right? If you stretch this out to infinity, this is 1. Is that clear? So a delta function which is very squeezed in one space, in the Fourier space, it stretches out completely. So this is squeezed, this is localized, this is not localized. That's the language used. Is that clear?
The second one is delta function.
This is delta function, right? So delta function is when you squeeze this, right? Like in the extreme case, you say this is just one point, it goes to infinity. If you go into the Fourier space of a delta function, this is just 1. Everywhere it is 1. So in the exact case, this will be just 1. All the way till minus infinity to plus infinity. So what is the Fourier transform of a delta function? A constant, right? It's 1. It's just 1. And what will be the Fourier transform of 1? It will be delta function. Right, they're related to each other. Okay. So this is how you want to start looking at Fourier transform. If you have a function, you want to think of, or any physical quantity, like usually we say causality is an example. Like causality means something happens before or an effect comes after the cause. how will that feature look like in a Fourier transform? So if there is a function which describes that, what is a function that describes causality? It will be a step function, right? 0 or 1. Right, with 0 here, 1 is there. So what is the Fourier transform of a step function? What is the Fourier transform of a sine function? These are the things you want to look at it mathematically, but we want to start looking at it more in the sense of physical nature of that function. What is the physics implying there? So one of the things that displays a role is polarization. So this is electrodynamics. Polarization. And that can be motivated by Gauss's law, Maxwell's equation. What is Gauss's law?
In differential or integral form.
Let's say differential form, very good.
The gradients or del dot E equals rho over epsilon naught.
Yeah. Let me write the epsilon out here. That's equal to rho. If I have a single atom, what is rho? So, or single electron, proton, let's say, a point charge. What is charge density for a point charge?
Here.
No. Point charge has a charge. So charge, this is charge per unit volume. A point charge by construction is existing only at one point. So it's a very extremized function.
Yeah, there's
So it's charge per unit volume. Yes, so it's a delta function. And this charge is what comes in place. So charge density for a point charge would be equal to the charge itself, Q, times delta function, which exists only at the position of the charge. So this is the position of charge. So if you solve this differential equation, so usually in electro, the whole of first few months in your electrodynamics course, what you do is give me any charge density, and I'll give you the electric field. So for a first point charge, what is the electric field? Point charge, what's the electric field? Coulomb's law, right? Q over R square. Here it will be R minus R naught whole square, right? But we are not going to work on that. That's solving the differential equation. That's Poisson's equation. That's what you study in electrodynamics. That's not what I'm going to do here. Instead, I'm going to motivate. So that's for a point charge. An atom, what is the charge for an atom? Total charge for an atom, neutral atom? 0. So what is the charge density for an atom? The neutral atom.
That's no charge, it has no charge density.
Again?
It has no charge, I'd imagine it also has no charge density,
So it has no charge density.
but that doesn't make sense.
So does an atom interact with another atom? It does interact. So if it is neutral, how does it interact at all? Let's say it's statics. Like since this is this equation, this is first equation, there is no time dependent. Or let's make it simple. Yeah. If there were two atoms that are really neutral, do they interact? No. The whole of chemistry is gone then if they don't interact. They do interact, but how do they interact? Even at a static level. Like of course, motion is a good point, and frequency is another point that we'll bring in. That's what whenever time dependence comes, frequency dependence comes. That's correct. But even just as a like water molecule, what is its charge on it?
It's like positive.
No, it's 0. It's neutral. Right? Otherwise, we will be attracted towards water, right? But ocean will be too charged, right? So it is neutral. But water molecule, how does it look like? Geometry of a water molecule? You know this,
Your,
yeah.
Hydrogen atom.
It's not symmetric, right?
Yeah.
So what does it have? It doesn't have a charge, but it has.
About
Rocky?
Yeah. Partial charge, but if there's a term,
Like a dipole.
Yeah, electric dipole, right? It has an electric dipole, so it is neutral, but it is a negative and a positive charge. Do not sit at the same place. So if there is a new charge that you bring or another another atom you bring in, that's positive and negative. These are like two magnets. Two magnets are neutral, magnetically neutral, right? North pole, south pole, north pole, south pole. But they attract and repel. Right? So atoms behave like electric dipoles. Right? They're slightly displaced between each other. Let's talk, that makes it a little difficult because there is a distance a, right? So negative charge is slightly away from positive. It's exactly like a point charge. Point charge is really not a delta function, right? It has some radius onto it. But we can take the extreme situation where it is really a delta function. It captures most of what we want. Similarly, a dipole, we will keep the property of a dipole, but we are going to have the negative and positive charges come onto each other. We'll talk about the limit where A really goes to zero. So an electric dipole is going to be equal to, so this is a dipole, maybe I should write that. So what's the charge density of a dipole, right? Electric dipole here? That would be equal to Q delta function of R minus, let's say this is R naught plus A, right? So this is your vector A, so if you say this is your negative charge, that's your positive charge. So that's negative, that's positive charge, and that's your A. This is R naught, and this is R naught plus. Is that clear? Right, that's your two points, and it is a negative charge that is sitting here. So that's your negative. And no, positive charge is sitting at R naught plus A. So this is minus, and then subtract it out. So this is Q times delta Q of R minus R naught. That clear? So two charges. An electric dipole basically is constituting of two charges. So the charge density will be 1 plus 1. They just add up. Is that clear how I constructed that? If I were to divide this out by an A, R minus R naught minus A minus of Q, or not Q. Oh, so hold on, this minus. So that's rewriting the same equation. I multiplied by an A divided by an A. And then this is just written in this form. So I took out a minus sign. Does this look something familiar? Like whenever you have a structure like difference in something divided by the difference in something, in the sense this is the difference in the position. Maybe let me write that down more clearly. This is R minus R naught minus of R minus R naught minus A. Then I'll be careful, so because I'll take the gradient of that, right? You don't divide by vectors.
That's a good idea.
No? Difference in something divided by difference in something? In the limit, something goes to zero? Differentiation, right? So this is change in the position or the function charge density as you change your position, that's derivative, right? So you can make this more precise. I said dividing vectors is not okay, so you can make it a directional derivative. This will be equal to minus q times a times the gradient of the charge density. This is a property of an atom itself. Like A, how far is the negative and positive charge separated? So what is the physical interpretation of A? This is any atom can be thought of as a negative and a positive charge, a center of negative charge, center of positive charge. They need not be adding up or at the same position. The average of that might be separated as slightly differently. And that's your A. So this is your dipole moment. This is your dipole moment D if you want. So this is minus D dotted with gradient of rho. Dipole moment is independent of the position. If the atom moves, you don't take a gradient of that, pull that in, call that the dipole moment. So this is minus of gradient dotted with P, where P is now going to be defined as dipole moment per unit volume if you want. So this is equal to dipole moment per unit volume. That means you have a lot of, think of a liquid of water, you're collecting all the dipoles per unit volume. Here you talk about charge per unit volume. Here you talk about dipole moment per unit volume. So the overall, the idea is that the dipole moment of a material is given in terms of the polarization at every point, polarization density of the material, and there is a negative sign associated with it, and how the polarization changes. Just to give you a physical motivation for this, historically, this played an important role. The way we are talking about it, if dipoles interact, so eventually atoms are interacting with dipole-dipole interactions, and if the dipole-dipole interaction is stronger, they will be solids under room temperature and normal room temperature and normal pressure. If they are not very strong, then they will be liquids, right? So reduce the interaction between the dipole-dipole, they will be liquid, and beyond that, it will be a gas. Now, and in about 1800, this was Faraday's time, it was very common to liquefy elements. You had 91 elements on the periodic table, and the goal was to liquefy each atom. It was very clear that if you make it colder, then it will become a liquid, and if you further make it colder, it will become a solid. So first idea was just to go from gas to liquid, and it was harder. Just to make it colder, it was hot. And imagine what are those elements called on the last column? Noble gases, right? Noble gases do not have a dipole. Right? So they are exact spherical shells. Think of the quantum model for an atom. So all the shells are spherically symmetric. So most of them are exactly spherical in shape. So that what will happen to their liquefying temperature will be very, very low. So almost to 0 degree Kelvin, they won't show their dipole moment so very clearly. So helium was the hardest to liquefy. So the last element that could be liquefied is helium, and that was in about 1900, 1910 or something. And the main reason was that they don't have a dipole. They don't have a very strong dipole interaction. If it exists, it's very, very weak. So in that sense, that's that gives you a physical motivation for what is going on. Okay, so we have a material P, and then we ask, this is polarization of a material. Sometimes, like helium atom, as I said, is having zero polarization. If you provide an electric field, what will happen to a neutral atom with, let's say, helium atom? What will happen to helium atom if you provide an electric field?
The charge is polarized.
Yeah, polarized. So we'll induce a polarization. This is a polarization of an atom that is permanent just because of geometry. Like water molecule is placed in such a way. So again, maybe I can draw a water molecule. Help me here. Water molecule, what is at the center? Hydrogen?
Yeah,
Hydrogen at the.
hydrogen, and then down to the bottom left and right, you get the
So
little,
this is positive, and negative. Is that how it is?
yeah,
Right, so this is like you have one dipole in here, that's another dipole, right? And resultant wise, so this will be a total, right? So the vertical components cancel. So a water molecule, as far as another water molecule looks like, it looks like something with a oriented dipole. It's pretty much like a magnet, electric magnet, if you want to see. But a helium atom doesn't have this. So a helium atom is practically, so this is water, helium molecule, or just helium atom, let us say, so just helium. So helium is just positive and a negative right on the spot itself. Both the positive and negative charges that constitute a helium atom, they are like this. Now you provide an electric field, what will it do?
Positive goes in one side, negative goes in.
Exactly, positive will go on one side and negative will go on the other side. So that's positive and negative, and now it has a dipole. You remove the electric field, it doesn't have a dipole. You provide a electric field, it has a magnitude, it has a dipole. That's pretty much like iron. Iron doesn't attract iron itself, but you provide a magnetic field to that, it behaves like a magnet. So that's pretty much what it is. This is not a magnet, but the moment you provide an electric field to it, it behaves like an electric dipole. Now we want to ask, what is an electric dipole? Is designed by P, right? That means there is an induced electric dipole. It depends on the electric field. So we want a model for that. Well, let's talk about that, and I want to keep this. We have a polarization. Now we want to talk about induced polarization. Induced polarization is P is equal to, often you would say, this is equal to some constant times electric field. We just write it this form. And usually typically this is a dyadic. It also depends on the direction of the electric field. Sometimes you provide the electric field in this direction, it will get polarized in an opposite direction. So more generally, this is actually a dyadic or a tensor ordered with this. For our purposes, for simplicity, let's take chi is simply 1. Like that means it's isotropic times chi. So that's just for simplicity. So that will make this chi times. This is called the susceptibility. For dimensional reasons, you also provide an epsilon naught here. If you're in SI units, you also provide an epsilon naught. And This is what you will often see written everywhere. This is correct. So what we are saying is that polarization is linearly dependent on the electric field. Polarization is linearly dependent on the electric field. Increase the electric field, more is its polarization. If the electric field is small, the polarization, which is intuitively very clear, it is linear, and this is a constant. But this, and now let's make this more precise. So P is a position dependent quantity. This is R and T. Right? And now you would like to say that this is a on the right side, there is an electric field and chi. Like, let me leave some space here. So chi has position and time dependence. We would like to know what that is. And electric field, we do know how it looks like. There is a position dependence here, and there is a time dependence, right? The electric field depends on position and time. If you were to think of this as time t, and this is also the time t, most naturally, what you would say is that this is also time t. Correct. But then you will immediately have some, at least logical issues as to this is instantaneous. Electric field changes here, and immediately the polarization changes immediately. So is this correct? And even position wise, is this R, and is this going to be equal to R? So we want to make this more precise. And the main idea is that what about the electric field at a previous point? Is it going to affect that at all or not? Like, notice that this is a molecule. It can depend on the previous past of the molecule, right? If you change the electric field, it takes some time for it to react. The response usually can take some time. It may not be locally dependent. It may not depend on another point, if as far as you provide the time for it to travel from one point to the other. So again, we want to talk in terms of time. In general, we should talk in terms of position also. For simplicity again here, let's not talk about the non-locality in position, just the time. So once you have t here, this could depend on everywhere in the past, and this has to be t minus t prime, and this should be t prime. So you're saying that even the electric field a little bit earlier in time can affect the polarization at the current point. Where will this integral go from? T prime. What are its limits?
Minus infinity to t.
Very good, right? Why t, right? It can go very much in the past. Like, the past can depend. Your current polarization can depend on very much in the past, we are saying, but it cannot depend on the future, right? That's causality, right? So we cannot go beyond this. So that's a challenge that comes in, and the moment you take that, the Fourier transform usually is minus infinity to plus infinity. All the mathematical ease that you have depends on this going from minus infinity to plus infinity. It just becomes more tedious to work with. But we cannot escape that, because we cannot say that future decides your present. So we have to force this in. So this is for simplicity. I'm saying this is R, and from now onwards, I won't write R dependence at all. We won't discuss the position dependence in it. Just so that there is simplicity in dealing with these integrals, I would like to write plus infinity, but at the same time, I don't want to spoil the physics. So I have to say that this is some function f of t minus t prime, and comma t prime. But to bring in the feature that it does not contribute anywhere beyond t, I say f is equal to where f is step function. Yes, very good. Right, that's equal to a step function of t minus t prime times kappa. That takes care of that integral feature. But you shouldn't forget that this step function is anything. So that's your polarization depending on the electric field. And now let's very quickly see. This will be an exercise in Fourier transform. This is a very maybe hard to interpret this equation because they are sort of correlated or coupled in a sense that at time t minus t prime it is t prime and you have to add up all these together. So they're convoluted, that's the word used. But you will notice that because of the structure t minus t prime here, this in the Fourier transform, they will be algebraic. We have already seen that in a differential equation. A differential equation in the Fourier space is algebraic, right? There is no derivative that comes in. Right? Derivative simply becomes algebraic. So that will be the same thing here. This integral will become algebraic in the Fourier space, primarily because of this translational symmetry. The idea would be whenever you have translation symmetry in Fourier space, things are algebraic. So let's verify this. Let's start from here, and now basically we will start from here, right? So P of T. So I think I have space there. I can go till here, right? Yes. So you're dealing with function P of T. It's equal to minus infinity to plus infinity prime position we are not worrying about. And epsilon naught is just for dimensional reason. I want to find the Fourier transform of this equation. So the point is, in this equation, how will it look like in the Fourier space? And the idea would be that each of these functions have a Fourier transform. F of t as f of omega, p of t as p of omega, and electric field will have an electric field. So every function has a Fourier transform. How do they look like? How does this equation look like in the Fourier space? So let's start with p of omega will be equal to, I start from the definition of the Fourier transform itself. So this will be dt dt. Yeah, dt minus infinity to plus infinity exponential of I omega t times of t. That's coming from this equation in here. Instead of f, I put in p in that. Fourier transform of this would be p of t. This substitute this integral in there equal that should be also correct. I substituted this in here and keep processing it, and I can transform everything into the Fourier space. So this also has a Fourier space, Fourier component in it. This also has a Fourier component in it. So it becomes multiple integrals, but we won't evaluate any of these integrals except using delta function. It seems like there are many integrals, but we will only use the delta function property to evaluate integrals. So keep doing this, we cannot do the t integral because there is t in here and we are doing a very generic function. We cannot do the t prime integral because the electric field is not very, this is a very generic function. So substitute this expression for the Fourier transform. Prime Fourier transform f of t, that's already t, so it will become f tilde in there, write that in here. So this will be minus infinity plus infinity. Bring in a frequency now, integrating, so this is d omega prime q pi e raised to minus I omega t prime. So the tilde of omega prime. Is that clear what I did? So this box here is this piece in here. Like I substituted using the definition of Fourier transform in here. Notice I'm not going to be doing any integral, I'm formally doing things. So, but that's a generic thing that you do in Fourier spaces. Do the same thing in here, electric field. Within this plus infinity d omega double prime over q pi e raised to minus I omega double prime t prime. Tilde. Hopefully. Yeah. Again, maybe do this as a circle. I just substituted the definitions in there. But now look at the time integral. There are two time integrals, two frequency integrals. The frequency integrals are not easy to do because they involve generic functions. They are doing it at a very generic level. But the time integrals, if you notice, they're all in exponentials. The time variables are purely in exponentials, they're doable. That's the main idea in Fourier transform. Frequency, we're not able to do much in frequency, but time is completely doable. So I'm going to do this time integral. So I collect things together onto the left. Make a double prime for 5. So the order of integrals has changed. Earlier we were doing time first and then the frequency, and now the or in the writing part, frequency comes first and then time later. F tilde can come out altogether, so that's omega prime epsilon naught times E tilde omega double prime. Because this can come out of the time integrals. The time integral dt. Let me write this as e raised to pi omega t. So that's this. And there is one more t piece in here. So this is minus pi omega prime t. Dt prime is e raised to pi omega prime t. Here it is minus pi. Is that clear what I did? I started from this expression. I'm basically rearranging my integrals. I haven't done any integrals. I just changed the order of the integrals. That is all that I have done. What is this integral equal to? The time integral t prime equal to. No.
That a delta function.
That's a delta function.
Right.
Remember we said here, whenever only an exponential comes, it is a delta function. And in this case, this was t equal to 0. But here we have a t integral and a frequency left out. So it will be a frequency on the left hand side. So whenever there are pure exponentials being added or integrated, that's a delta function. And it will be what will be the argument of the delta function whenever the exponential argument goes to 0. So here the exponential argument goes to 0 whenever omega is equal to omega double prime. So this integral is equal to 2 pi. So this integral is equal to 2 pi times delta function of omega prime minus omega double prime. That means whenever we do the omega integral, it only contributes whenever these two are equal. The second integral is also doable. This is equal to 2 pi delta of omega minus omega prime. So we're both exponential, pure exponentials going from minus infinity to plus infinity. That's a delta function. Yes.
Do those combine into a delta of omega minus omega double prime?
No. If you integrate, no, they do not. A simple answer is no. Two delta functions are very sensitive. Again, imagine that this is getting a contribution at omega prime, right? This is omega, and this is getting a contribution at omega double prime. So this is equivalent to saying that it will contribute at 2 points. But by any chance, if this was equal to this, right, then you would say this 0 comes in here, so it's a delta function of a 0. Right? That's not nice. That's a derivative of a delta. So it's not the normal divergence, so it's a derivative of a divergence, which can be handled, but one should be careful about that. It's a bit sensitive in there, and it does come across. You do come across those issues in another context. Here we are fine. If you have delta function, how do you integrate omega prime in here? What do you get when you integrate an integral that has a delta function?
You just get omega.
You replace all the omega primes with omega. Replace all the omega double primes with omega prime, but omega prime is to be replaced with omega. So this whole integral collapses. Already we have done 2 integrals. The other 2 integrals also collapses. We just have to replace all the omegas with omega primes and omega double primes with omega, and that's equal to, so remember 2 pi cancels out, and this becomes f tilde of omega prime, or omega now, times epsilon naught electric field. And now you would say, oh, f tilde, f was defined as a step function times chi. Right, so notice the simplicity in here, this was an integral. Right, the polarization at one point in a material is dependent on the electric field. This is very nice, it is a proportionality, it's algebraic. Only in the frequency space, so here it was convoluted. Like all the past was affecting you, so the whole year, like it's much easier to live life if only the present was affecting you. But when you say that, oh, my grades from first grade is going to affect me today, that's harder, right? So this is what it is saying, that here all your grades matter, but in the frequency space, it's only the present that is going to affect you. So there is a lot of convenience in working when you're in the frequency space. But where has all the information of the convolution gone? Physics cannot just, you cannot forget about the past, right? So where did that go in? It is inside the step function. This is not f, or this is not the polarized or the susceptibility, right? The susceptibility has a step function inside there, and the step function has the details about the causality. So where is causality here? Remember there was a the stop in there. That's inside in here. And so now we have to ask, how does causality look like for susceptibility? Just this piece in here, how does it look like? So first point is that polarization. So when you do experiments, why do you work in colored with color, primarily because it becomes algebraic. Right? Your equations are algebraic. When you're working with red color, all your red colors, all the equation is only frequency dependent on the red color, except for the susceptibility. Susceptibility will have information about all other colors. So how does it have it? Let's talk about that. So now we say, now we are going to concentrate only on this. And primarily the step function itself. How does this frequency dependence look like in the Fourier space? The question we ask is a step function. This is also called Heaviside. Step function. It's going to be. It is t minus t prime, but I can set one of the variable to be 0. This will be 1 if t is greater than 0. This is equal to 0 if t is less than 0. And we are wanting to ask if I want to Fourier transform this, like f of omega, I have a step function that I have to Fourier transform. So let's ask the simple question: what is omega equal to? The Fourier transform of your step function. This is in more physical terms. You will say this is causality, right? This is what was used to use causality in this expression. So how does a step function nature look like in the Fourier space? So we will use our Fourier transform definition then. Omega is equal to, this is an frequency, so you will integrate over time, and that is exponential of I omega t. This is t, and you go from minus infinity to plus infinity. This is either a 1 or a 0. This is equal to 1 or it's 0 whenever t is less than 0. That means this integral, whenever this integral is less than t, it doesn't contribute. So this is 0 to infinity et e raised to I omega t. That. Because in this region t is greater than 0, t is the lower limit is 0. Yes.
Is the step function defined when t is equal to 0?
No, it is not. So it is sort of.
Because of that discontinuity.
Yeah, there is this discontinuity. So you can ask what is step function at this equal to. It is practically not very well defined, not at least as a continuous function. In the limiting form, you can give it some structure. But if you have any physics that really depends on theta equal to 0, you have to be very careful. Then you again go back and redefine this function and make it a continuous function, and there are ways to do that so that in the limit this gives you that answer. It becomes more tedious. For our purposes, this should be sufficient, but again, it will show up. It shows up in various places that that discontinuity will matter. Okay. So that's your integral. What is that equal to? That's not a delta function.
Yes.
Because it's 0. Yeah, I've been saying that so many times. So that this is misleading because it's starting from 0, right? But if it is 0, then you can use your standard approaches and try to do this. But be careful, right? Let's try to do this our standard ways. So these are exponential. So it is exponential I omega t divided by the integral of that argument, right? And then you have to do t equal to 0 and t tends to infinity. So that's all you do. And you should see a problem here. that at t tends to infinity, what is the exponential function at t equal to infinity?
No, you didn't, I know.
Not infinity, but it's not very well defined. These are cosine and sine, so surely not infinity, but they're oscillatory. So you really don't know whether it is +1, -1. So it is not very well defined. So that t equal to infinity, you don't know, but t equal to 0, you surely know that this is 1 over I omega. So now we are stuck at how do you proceed. So usually, like earlier, the question was what happens when somewhere in between something is happening. If it is not very well defined, put in a parameter and take the limit that goes to 0. Right. So let us put in a parameter. So this is now. So this is the function again. So I'm going to redefine this in the following way, because otherwise I cannot proceed. I'm completely stuck here. It is just my inability that we cannot proceed. So we try to do some damage control. And so you say that this is equal to e raised to time. I cannot do much, but maybe with omega I can say plus I delta times t. So what I did effectively is I times I is a minus I, so this is equal to minus infinity to plus infinity dt exponential of I omega t times minus delta t. This is convergent. For very large t, remember what was happening at t equal to infinity, this was not well defined. Yes. But this function for very large t, it practically kills it. Right, so it will make it, this will help me make this well defined. But then what is delta? I say that this is I want to have limit delta tends to 0. This is sort of a cheat we are doing, but the hope is that with that limiting form we can have some or we will be able to proceed. Is that clear? Yes.
When we were doing with the heavy sides, we had the limits of 0 to infinity. Why did we use negative infinity to infinity when we parameterized it?
Oh, because that's a mistake. Thank you. Yeah, thank you, yeah. Thank you for pointing that out. Okay, now this should be clear, very clear, okay. Okay. This integral, now we do it the same way again. This is just that omega plus I delta has to be taken care of. So this is equal to limit delta tends to 0 and your exponential of I omega plus I delta times t divided by omega I omega plus I delta. And you're again evaluate this at t equal to 0 and t tends to infinity. That's the same integral, except instead of omega, I have put in omega plus I delta. And now you notice that at t tends to infinity, this is well defined. At t tends to infinity, how much is this equal to? When t is equal to infinity, what that happens to this function?
Does it go to 0?
It goes to 0 because it is of this form, right? Exponential of minus delta t is there. So this is equal to 0 this time, minus of 1 over I times omega plus I delta. And I shouldn't forget the limit delta tends to 0, right? At this point, it is very tempting to say that, okay, now I'm in the Fourier space. Delta is equal to 0, but omega has to be very small, so set that to 0. Is that correct? And why is that not correct? Because if you set that to, if you want to set that to 0, you want that to be less than omega. But there is always a frequency with which is lower than that, right? You can have 0 frequency, for example. So 0 frequency is, by the way, what does 0 frequency mean typically, physically? In time, how will 0 frequency look like? Huh? Constant, yeah, but tell us better. Yeah, you're right. So the main idea is that, remember, I think I was telling something that is very small in time gets very big in frequency, right? So there is a, if the range of the function is small in time, it will be very big in frequency. So in frequency, if you're making it small, it will become very large in time. That's what he said, it is a constant. So it is static. So whenever you're thinking of electrostatics, or when we say statics, what that means is that time is not coming into picture at all. So time is practically constant. It starts from minus infinity, goes to plus infinity. There is no time dependence. So the time dependence is a constant. So in frequency space, what will happen? Only the 0 mode will contribute. Only the 0 frequency will contribute. So one has to start putting that together. So here we cannot really set delta tends to 0 there. But let us now verify if this is the frequent Fourier transform, we should be able to get back our step function using that. So let's do the inverse transform as an exercise. In the last 5 minutes, I have. But assuming that contour integrals is good with you all, so probably it will be easier. So now I have step function, by the way, just recollecting. So this is 1, 0. So this is t greater than 0. This is t less than 0. In the frequency space, this will look like 1 over I minus 1 over I actually. It's minus 1 over I, 1 over omega plus I delta. We started from here and got this. Let's do the opposite just as a verification that this is all consistent. So let's do the integral. So d omega over 2 pi e raised to minus I omega t. And now we go from the whole. So what should this give you? They should give you the step function, right? That's a definition of one layer below. This is the Fourier transform definition, right? This should give me the step function. But let's verify this, whether really this works or not. So this is equal to minus 1 over I minus infinity plus infinity omega over 2 pi. And you have exponential of minus I omega t over omega plus I delta. We know how to evaluate these kind of integrals using contour integral, correct? So this is on a real line. So let's have a complex plane Z. We are integrating, so no, not complex plane Z, it is omega, complex omega. And we are going from my this way or that way, and where is the pole? Omega is equal to minus I delta, so that's your pole. So, but notice there is a minus I omega in here. So when does the upper contour help, and when does the lower contour work? So this is C1 and C2. There is another one. At one time you do only one of them, right? So this is C3. Either you can go C1 plus C2 or C1 plus C3. That's a new integral nowadays, and the pole would be equal. So you can say that integral d omega over 2 pi on the C1 plus half C2 e raised to minus omega t omega plus I delta. This will be equal to what are the poles in there? How many poles are inside the contour in this case? There is no pole inside of the contour, so that's equal to 0. But when is that the case? You also need the situation that C2 should go to 0. For C2 to go to 0, you have to write this as cosine theta plus I sine theta. And this will give you plus I sine, so it is plus factor coming in, so it should be t less than 0. So this should be the case when t is less than. And do the same thing for C1 plus C3, C1 plus C3, omega over 2 pi. And that will be equal to 2 pi I times whatever is the value of this integral at omega equal to minus I delta. So let's see that. So this is equal to minus 1 over pi, and that is a 2 pi, 1 over 2 pi. And when omega is equal to I delta, I have to substitute the values in there. So this is equal to exponential at I delta. So this is minus I times I delta times t. But also notice C1 plus C3 is going in the counterclockwise sense. So there is one more sign that is coming in. This is from the sense of the contour. In what direction the contour is going in. Together, they all go away. In the limit, now at this stage, at the very end, you take the step idea that delta is going to 0. So this is equal to 1 if t was greater. This is the contour, but you can show that the C2 and C3 part is really 0. And that is what I use to write t less than 0 and t greater than 0. So you do indeed get step function. We have only talked about the step function here. The details of how it has to do with reflection coefficient and absorption coefficient. What it will imply is that reflection coefficient and absorption coefficient, you don't expect it to be related for a material. But it turns out there is an exact relation between how a material reflects at a certain light and how much of it is absorbing it. There is a mathematical relation for that, and that's called the Kramer's chronic relation. We won't do that in detail here, but here this was an idea to how to bring in that causality part in there. From this, you have to go further to derive Kramer's chronic relation. I'll stop here.